Okay, hello everyone. So I want to complete our discussion of Fermi liquid theory today, and also note that there's a new problem set on the website. This is on magnetism, ferromagnetism, and antiferromagnetism in insulators. Not a topic that I'm covering in lectures, but the problem set guides you through some analysis of the excitations of such magnets, and you can also discuss it in section with Ryan. Okay. So let me summarize where we were in Fermi liquid theory. So the idea of Fermi liquid theory is that there's a set of elementary excitations, which we'll now just call quasi-particles. They include quasi-holes. We'll take a more general perspective. And then these are constituents from which you can build all the low energy states. But it turns out to be useful to imagine that the quasi-particles are also present in the ground state, because then it becomes easier to think in terms of quasi-holes and quasi-particles in the same formalism. So you imagine that there's some zeroth order quasi-particle distribution function, which is 1 inside the Fermi surface. So that's this function here, and 0 outside the Fermi surface. And this is the ground state. I mean, this is just a idealized representation of the ground state. We don't really know what the ground state wave function is. We don't even know what the quasi-particle wave function is. So we just postulate that we can think of the ground state as a fiddle state of quasi-particles. Then the actual physics will be our description of the excitations. And the excitations, say at some finite temperature, will be the actual distribution, which may end up looking something like this. So we'll call this NQP without a zero. And the actual quantity that we'll be interested in will be delta NQP, which will be NQP minus NQP0, where, of course, NQP will very naturally in the theory, the way we formulate it, because we're going to think of the quasi-particles as essentially free fermions, as we'll see today. So it'll be automatic that NQP will be between 0 and 1. And that's, of course, also a property of NQP0. It's either 1 or 0. And so you say it will be automatically built into the theory that delta NQP is going to be negative below the Fermi surface and positive before the Fermi surface. Okay. And the other important point is that this delta NQP is of order 1. It's unity. It's of order 1. But it's order 1 only in a very narrow window of momenta. So there's a very narrow window of momenta here, where this is of order 1. And outside this window, it's 0. And that's really the small parameter in the whole calculation, the fact that it's of order 1 in a window of order temperature. Okay, so that's the basic idea, that these are exact eigenstates of the Hamiltonian, which describe the complete set of low energy excitations above the ground state. And the remarkable fact, and really this is the physical assumption, is that all of the many body excitations at low energies can be built out of just adding together single particle excitations. And that, if you wish, is a definition of what you mean by a quasi-particle or an elementary excitation. Okay, so our degree of freedom is delta NQP, and now we just dropped the QP in our discussion, at least in the notes. And then you write down an energy, and this is kind of where I ended last time. The energy for some delta N of P is given by two terms. There's just the sum of the energies of the quasi-particles. But to an equal degree of accuracy, we also have to include the fact that there can be shifts in the energy. So if I have 100 quasi-particles already in my system and I add one more, the energy cost for adding that extra quasi-particle will depend on the other 100. And that's dependence is encapsulated in this function fpk, because it will also depend on how far apart the quasi-particles are on the Fermi surface. But notice, we're just treating this as some kind of density, a classical density. There's no actual scattering in this term here. It's not as if when you add a quasi-particle, some other quasi-particle gets scattered to another state. We'll consider that shortly, but that's not included. We assume that those processes are not active, and any kind of scattering is a virtual process that's already been built into the definition of the quasi-particle, because these are eigenstates of the Hamiltonian. Okay. All right, any questions? Okay, so now that we have this Landau functional, we can compute various things. And, again, you can read books on, in fact, there is a book by Nozière, compute all kinds of things starting from this Landau functional. We'll just compute two things. One is the specific heat and the other is the compressibility, just thermodynamic quantities. There's a lot of other things you can do in the framework of Landau from liquid theory. Okay, so we just assume that we are at some low temperatures, but an equilibrium. So we're going to make the assumption, which we'll shortly show is correct, that the distribution function of the quasi-particles, the actual distribution function here, will be just the Fermi function, where here I'm just going to put in the energy of each quasi-particle. So that's not immediately obvious that's the correct thing to do, because I just said, when you're at some temperature, there's some gas of quasi-particles floating around, and that gas is going to change the energy of the extra particles. So it could be that when I add another particle, its distribution function will be different because its energy will be different. All right, so that's the kind of thing you do have to worry about. But it turns out not to be true. And the reason is the following. The reason is that in thermal equilibrium, this function, and if you use this identity, f of minus e is 1 minus f of e, and also the fact that EP is also an odd function near the Fermi surface. So you can show that this thing, delta n of p, is an odd function of the radial momentum. Okay, so if you go across, so in this picture, if I plot delta n of p in the radial direction, so if I make a plot of delta n of p, and this is my origin here, I'm going to measure momentum from this point, pf, and this is, and that's let me plot delta n of p minus pf. Well, it's negative here and positive there, and you can just see from the structure of the Fermi function, it turns out that the Fermi function is such that its derivative, I mean, this difference is an odd function, and that's not totally obvious. Didn't have to be that way, but it is. So it comes out looking something like this. So this function is an odd function in thermal equilibrium. So this is odd for n QP equals Fermi function. Okay, so why is that important? Well, now let's look at the energy function now. So if I add in another particle, add some momentum p, so add in a particle at momentum p, its energy is going to shift due to all the other particles in momentum k. So I have to do this integral over k of delta n of k to figure out how much the energy of particle P changes. But the integral over k has an angular dependence, which is very complicated because there's an angular term here. But it also has a radial integral. The radial integral over k will combine with this integral to just give me 0, because this thing is an odd function of k about the Fermi surface. So in fact, there is no shift. And all this fancy Landau functional doesn't contribute. Yeah, so as I said, the second term in the Landau functional vanishes to the leading order that we are studying. And therefore, at least in thermal equilibrium, these Landau quasi-particles are just free particles. So it's just as if you have a free electron gas. The only difference is your EP is not the bare EP, it's the normalized EP. So for the specific heat, in 295A or some 100 Gattis-Stockmack course, I presume you've computed the specific heat of a free Fermi gas. It's given by this very general expression in any dimension where G of 0 is the density of states at the Fermi level. This is the leading behavior when temperature is much smaller than the Fermi energy, which is always the assumption in Landau Fermi liquid theory. And for the Jellier model, indeed, 3 dimension is related to the effective mass. So the only difference to the specific heat would be that you just replace the mass of the electron by m star. So this is a very powerful statement, which people use in the real world all the time. People measure the specific heat. What they measure is sometimes called the gamma coefficient. Gamma is CV over T. So if there's literally thousands of papers, people can find a new material, they measure the specific heat, they measure gamma, and they have some other way of figuring out what PF is or something about the shape of the Fermi surface. And so therefore say, m star, I've measured m star. So the specific heat is regarded as a measure of m star. It's directly measurable. It's not, there are no corrections from to the gamma coefficient from the interactions. Other than that, those go into the definition of m star. Okay, so, and that turns out to be one of the few quantities which is so nice and simple. But most other quantities do have a difference. And the simplest one is the compressibility. So the compressibility asks what happens when you change the chemical potential a little bit, how much does the density change? And now as you're moving the chemical potential, you're changing, it's not particle hole symmetric. So the Landau parameters will have an effect. So let me show you how that works. So what would you say? So let's imagine that you change in the underlying Hamiltonian mu to mu plus delta mu. So then your EP had a mu in it. For example, here, when we started out, you had some band structure and then you subtracted the mu in EP. So your EP will change, where did it go? Yeah, there's the mu there. So there'll be a change in EP to delta mu. So in the Landau free energy functional, this EP will have a minus delta mu. So now I can ask, what is delta n of once I change the chemical potential? Let's imagine I'm from non-zero temperature. Well, so when I change the chemical potential, then I will change the EP and therefore I'll change the distribution of all the particles. So each particles will then come to equilibrium in some other distribution. And that distribution will be in the in kind of a Hartree sense. The energy of any particle will depend upon the distribution of all the other particles. I mean, I kind of said this in words for the specific heat because that term didn't matter. So very generally, you can say, as long as you're in thermal equilibrium, that you can define a quantity EP star, which is how much the total energy changes if I change the distribution function a little bit. So I just add a few particles to some already existing set of particles. So this is the variational derivative of the total energy to delta n of P. So that's what I call EP star. And EP star has 2 reasons for changing. One is that EP changes, of course. But also, they could, there's all the other particles, and their presence will change the energy of your particle momentum P. So all the particles momentum K will change the energy of the particle at momentum P. So this is very much like what you do in Hartree theory. In fact, this is exactly like a Hartree shift, except this Hartree shift here is exact. There's nothing else at low temperatures. All right, so this, and the other thing to note is that there's a factor of 1/2 out front here, and that 1/2 disappears when you take the functional derivative, because there's two terms here. You have to take the derivative with respect to, as usual. All right, so that's what you define an EP star to be, and the claim is that, that's really the formulation of Landau theory, that the new distribution function will be the Fermi function of EP star. So apart from the shift in the energy, they'll be in thermal equilibrium. Okay, so these are the equations you have to solve now. You make a change delta mu. Delta mu causes a change delta n, and delta n then determines EP star, and EP star determines delta n. So there's like a self-consistent loop here, but this is not surprising. This is exactly what you do in Hartree theory. You assume some expectation value of some operator. From that, you determine the energy of the electrons. Then you close the loop and you determine that expectation value. And that's exactly what these two equations are. You make a change in delta mu, that determines delta n. You make a change in delta mu, you assume a change in delta n, that determines EP star, then you compute delta m and make sure it's self-consistent, okay? All right, so that's just a little bit of algebra. And in this case, you can solve the self-consistent loop analytically at low temperatures, okay? Because the form of these equations is very simple. So let's see how that proceeds. Okay, so we're just going to work at 0 temperature. So what we're going to do is take both equations and just expand them to first order in delta mu, and presumably delta n will also be proportional to delta mu. All right, so then what happens is the following. So if EP has a small shift due to delta mu and delta n, and at 0 temperature, this is equal to that. So delta n of P will be, so I can just write this as, so this implies delta n of P is dF dE and delta E. And then you use a few simple properties that dF dE at low temperatures is a delta function. So, and this delta E, we're going to assume delta E is going to be some constant times delta mu. We don't know what that constant is, so let's assume it's some constant A. So therefore, I can write delta n as some A times delta mu times the delta function of EP. Okay, so that's our assumption that delta n of P looks something like that. Change in the distribution is a delta function on the Fermi surface. And A is the constant that we need to determine. So what is A? Well, you just plug this equation back into this equation, and you expand everything to linear order. And when you do that, you find everything is self-consistent, and you get an equation for A. So A is equal to 1. This 1 comes from this term here. Okay. And then when you make the change delta n over here, you get this term. And so now this is an equation for A. Now the assumption here is that when I do the sum over K, the answer will be independent of P. If the answer is not independent of P, then it's more complicated. You have to assume that A is even a function of P, which you can do. But if you have spherical symmetry, then this is correct. So I'm just going to assume that. In general, it's a little more complicated. Okay. So if you have circular or spherical symmetry, this is the equation. Now that's a very easy equation to solve. So A is 1 plus this in the denominator. And so finally, I can then just compute dN d mu, which is the compressibility, which is the change in density, which is this quantity divided by delta mu. And using this algebra, this is what you get. And then finally, this thing is just nothing but the density of states at the Fermi level. So that's the final answer. So dN d mu for a free Fermi gas is just the compressibility. This is something we discussed way back when. And now this is not, and G of 0, as we just saw, has an M star factor on it. G of 0 also depends on the interaction because of M star. But now there's an additional correction. That's not the complete answer. So when you measure the compressibility, it's not just sufficient to just assume that you can just replace the electron mass for the quasi-particle mass and you got the answer. There's an additional correction, and that's the Landau correction, 1 plus F naught in the denominator. And F naught is basically the spherical average of the Landau parameter on this Fermi surface. Okay. Yeah, so that's the basic answer. And there are similar corrections to, spin susceptibility. Then you get an F naught, which is in the spin, which has, you have to put the spin indices back in, and so on and so forth. Velocity of sound and various other excitations of an interacting Fermi gas have some dependence on these Landau parameters. But the bottom line is really, in the end, the calculation that you have to do is basically like a glorified Hartree-Fock. I mean, not even Hartree-Fock, glorified Hartree calculation. It's just like a Hartree shift to the energy. But the remarkable thing is that it's an exact formulation of everything. Any questions?
Severe?
Yes.
So when you wrote delta n in, at the beginning of the lecture, it seemed that delta n is continuous, and it's kind of confusing because the n at the finite temperature is continuous while the n at 0K is discontinuous. So how can the subtraction give the continuous one?
You're right. Thank you. I think this picture is not correct. Sorry about that. Yeah, I didn't do the subtraction properly. Thank you very much. I think this ends up looking something like this. It's discontinuous here, and then it looks like that. Thank you. It's still an odd function, but it's discontinuous, right? Thank you.
Thank you.
And at zero temperature, it becomes even more singular because it's a delta function and so on and so forth. But anyway, but if you work at finite temperature, yeah, I mean, this is why you always work with this quantity, not and then you go from there. And the discontinuities all take care of themselves because they're properties of the ground state. Okay, but yeah, great point. Thank you. Sorry, I missed that. Okay, so now I want to, get some mileage out of all this formalism we developed: Green's functions, Wick's theorem, self-energies. We wrote down these diagrams. Can we relate Landau-Fermi liquid theory, which really, in principle, can be derived without even knowing about diagrams? But is there a connection? Okay. Indeed, there is, and I'm sure that Landau secretly worked out all the diagrams before just wrote down the theory with pure thought, because you need diagrams to check that these assumptions are indeed correct at every order. But afterwards, with the benefit of some hindsight, you can guess the answer. But let's just now take a more pedestrian point of view and really think about it from diagrams. So we had this, I'm going to use Matsubara frequency diagrams, and just to remind you, to get the real frequency, you just do an analytic continuation in the frequency plane. Okay, so the Matsubara, the general expression for this thing is this, where sigma the self-energy, which will depend both on the momentum and the frequency. So what does it mean to say that you have a quasi-particle? So the quasi-particle assumption is a very definite statement about the structure of this Green's function in the complex frequency plane for P next to, for P close to PF. So if I, draw the frequency plane, this is the frequency plane Z, and the I omega endpoints are over here on the imaginary frequency axis. But I want to think about what happens for Z close to the real axis. And what we have learned is that this Green's function, you just analytically continue in Z. Now, so momentarily, if I ignore the self-energy, if I just ignore this, at least it's frequency dependence. It could be any function of P, but any function of P in the self-energy I can absorb in the redefinition of EP. So this EP is the actual bare electron dispersion. So the frequency independent part of the self-energy, which is why it's called the self-energy, I can just absorb into redefinition of the energy. Okay, but apart from that, so let me ignore any frequency dependence here. So if I ignore any frequency dependence, what I see about this function, it has a very interesting feature. It's called a pole at Z equals EP0. Okay, so there's a pole here. So this is, there's a pole, say, here. I mean, it's right on the real axis, but I'm going to draw it just a little bit above. This is for P greater than PF. There's a pole. And there's a pole also for negative frequency for P less than PF. Okay, so that's the free particle or Hartree-Fock answer. If you do our Hartree-Fock theory, carefully, this is what you'll find, that the pole survives. It's just that the position of the pole move around, but the pole goes through zero frequency exactly on the Fermi surface. Okay, so now what happens when you go beyond Hartree-Fock and you try to include more complicated processes? Well, you'll find that the pole actually it moves off the real axis, and in fact it goes into the second Riemann sheet, if you wish. So really the pole, because the Green's function as we defined it is analytic everywhere, it's got a branch cut on the real frequency axis. So the pole, however, moves a little distance away to this point, and I'm drawing it as a dotted line to represent that it's actually in the second Riemann sheet. What I mean by that is, you analytically continue here, you'll find everything is just fine, and then you hit the real axis, and then you have a discontinuity on the real axis, and then when you go down there, again, things are fine. However, if I analytically continue from here and I keep going, and I ignore the fact that the definition of the function changes from the Lehmann spectral representation, then I enter the second Riemann sheet. And in the second Riemann sheet, there'll be a pole. And what I'll find that the pole will move off the real axis to some point, and this distance I'm going to call gamma p. So this distance here, that's gamma p. So that's written over here. I assume that there's a pole, which is, and it's in the bottom half plane because there's a z here, and gamma p has to be positive for when you come continuing in from the top half plane. And yeah, the subtleties about the energy structure, don't worry too much. Many of the books don't even get it right. But let's just say in some complex plane Green's function, there's a pole which has an imaginary part gamma p. And you can think of this imaginary part as kind of the decay of the quasi-particle. So you put in an electron that creates a quasi-particle, and the quasi-particle moves in a straight line for quite a while, and after a while it scatters off other particles, and it becomes part of it completely loses memory of where it came from. So it kind of decays into some continuum of excitations. And that decay rate, how fast that happens, you can determine simply by taking a Fourier transform of this in real time, is basically given by gamma p. So you can think of gamma p as the decay rate of the quasi-particle. It's actually twice the decay rate, but let's not worry about that. So gamma p is the decay rate of the quasi-particle. So what we want for the idea of a quasi-particle just moving with a fixed dispersion EP to be sensible, what we want is that gamma p is much, much smaller than EP. So that's really the key assumption of Fermi liquid theory, that there's a pole in the complex frequency plane for momenta p near the Fermi surface. And this pole has an imaginary part, which is much smaller than its real part. So in other words, the particle moves on for quite a while before it scatters. Okay, so that is in fact the quasi-particle then. And this gives you a prescription, in fact, for computing it. So now I tell you, now I just tell you, Landau just postulated that such a pole exists with this property. And then he proceeded to completely set gamma p equal to 0. We can do a bit better in principle if you could compute the exact Green's function and look for its pole, maybe on a computer. We can read off not only the quasi-particle dispersion, but we can also read off its lifetime, which was set so gamma p was equal to 0 in Fermi liquid theory. And there's another thing we can read off, which is this a residue of the pole. So the residue of the free particle, was just 1. But now when you include the sigma of p, there might be, some frequency dependence and momentum dependence. You pull that out so that the coefficient of the z is 1 here. So this coefficient is 1, and that by definition, and you can arrange that by choosing your zp carefully. So there is another number that you get out, which is called the quasi-particle residue, which is zp. And what is that? Well, that, roughly speaking, is the square of the overlap between a bare electron and the renormalized electron, right? So the way you can kind of think about this, add a page. So you're computing, you're adding an electron. So you have some ground state. You add an electron, C dagger P of T, and then you annihilate it a little time later. Okay. And what we're going to say is what happens is that when you add the electron, this creates a quasi-particle state, okay, which is going to move freely. But there's a matrix element. It doesn't create exactly the quasi-particle state. It creates a quasi-particle state with some matrix, which we'll call Z. So then we compute this Green's function by just computing this, assuming the quasi-particle is a free particle. And what I will get that this is equal to Z times E to the I, the energy PT, so the oscillatory behavior of a free particle with some gamma T. Okay, so this gamma term we throw out is very weak. This tells you there's a quasi-particle. And this Z is then the overlap, So what we then learn is that Z is the square of the overlap between bare electron, adding a bare electron, and the quasi-particle. so you have this picture that you have a an electron here with a cloud of holes, electrons and holes around it. That's the quasi-particle. And if this cloud is very big, then Z is very small. Okay, but it's very important to distinguish Z from gamma. Okay, and this gets a bit confusing. Z can be very, very, very small. That just tells you that the actual quasi-particle is very different from a bare electron. But it's, it could be 1 over 1,000 or something. It was really small because the wave functions are so different. But at the same time, the quasi-particle in end of Fermi liquid theory could be excellent because that new quasi-particle, once you create it, lives for a long time. So what really determines how good Fermi liquid theory is how small gamma is. It has nothing to do with how small Z is. So Z could be very, very small, but the quasi-particle could be still very well defined because gamma is small. And in fact, that's what happens in the heavy fermion compounds, as we're going to see in the next chapter, that you get these renormalized heavy electrons, which have a mass 1,000 times the mass of an electron. But nevertheless, they live a long time, and Fermi liquid theory works extremely well. Okay, it's only when Z is exactly 0, then Fermi liquid theory breaks down and you get non-Fermi liquids, and that will be the last topic of the course to talk about such states. Okay, right. What was I going to say? Yeah. Okay, so that's how you identify then a quasi-particle in diagrams. You just compute the self-energy, and you have to go to higher order than we have actually gone, but that's real pain in the neck. You have to compute a 2-loop diagram. If you want to see an honest computation of a 2-loop diagram, it's in the textbook. There's several pages computing this kind of thing very honestly, but it's a lot of work, and I'm going to take a shortcut in a few minutes. I also should mention that there's the rest of the Green's function, in addition to the pole, that's called the incoherent part. That's all kinds of other excitations you create when you add an electron to the system. You create a quasi-particle with a certain amplitude when you add a bare electron, and you create lots of other things too. But those other things don't give you this clean or free particle behavior. So that's why you just throw those out. Okay. So in fact, it's possible to measure ZP, this quasi-particle residue, because it's related to something very interesting. It's related to the momentum distribution function. So let's compute the following quantity. This is the number of electrons, not quasi-particles. That's why I put an E here. So whenever I'm referring to bare electrons, I put an E in the distribution function. So this is just the number of electrons with momentum P. Now for free electrons, I know that's very simple. It's just 1 below the Fermi level and 0 outside the Fermi level. But let me compute this in an interacting electron gas. Okay. So I have to compute it by computing this integral of the Green's function. That's the definition from the Green's function technology. So now what is this Green's function? So now I'm going to assume that this Green's function has this form, that it has a pole which is close to the real axis, and some incoherent piece, which I don't know much about, but it's a very smooth function near the Fermi surface anyway. And this pole has the property, as I approach the Fermi surface, then the EP goes to 0, but gamma P goes to 0 even faster, as we'll see by our computation in a few minutes. So gamma P, even as EP goes to 0, so EP, gamma P will turn out to be about an EP squared. It's even smaller. So as I approach the Fermi level, this pole will kind of come in, and then it's going to kiss the real axis and then go back out. So I have to then figure out what does this process of this pole hitting the real axis imply for this particular integral. Okay, so now you can evaluate this integral, and then it's a little tricky, but it's not that hard to figure out what the answer should be. So the important point is, as far as this integral is concerned, since gamma p is so small, let me just ignore gamma p. Then as far as if I ignore gamma p, then this is exactly the computation for a free particle, except I have an extra factor of Zp. So what I learned from this is because of the consequences of this pole crossing zero energy, there's a discontinuity in this function at the Fermi level. So Ne of p has a discontinuity, but the magnitude of the discontinuity is not 1, it's Zp. All right, so I can draw a picture now what Ne of p looks like. So this is kind of what it would look like in your favorite experiment. We'll go at 0 temperature now. This is the Fermi momentum. It would have a discontinuity here, and then go on this way. And the strength of this discontinuity is Z. Okay. And of course, this means that since Ne of P is bounded between 0 and 1 rigorously, you must have Z was strictly greater than 0 and less than or equal to 1. And so there is, so that's another beautiful result. There is a Fermi surface. And you can see it in an experiment. All you have to do is measure the number of particles in momentum P. And that's kind of thing is routine in photo emission experiments today. And in that measurement, you would see then what's called the momentum distribution cut in the photo emission, or MDC. You would see a discontinuity in this function right at the Fermi level, as of course it's not strictly discontinuous at finite temperature, but it becomes sharper and sharper as temperature goes to 0. And so the Fermi surface, the idea of a Fermi surface is completely well defined, even in a strongly interacting electron gas. In fact, it's also defined even for a non-Fermi liquid, but that's another story that I don't know if we can get to towards the end of the course. All right, so that's one of the results we get. And all of these results really follow from this very strong assumption that gamma p is much smaller than EP. This imaginary part of the pole is much smaller than the real part. Okay, so can we estimate gamma p? Well, to honestly work out gamma p, you have to do the two-loop Green's functions, which I don't have strength for. But you can do a simple calculation using Fermi's golden rule. So basically, you imagine that you have a bunch of quasi-particles, which are given by the Fermi distribution function. So we can just assume they're ordinary free particles, and they're all occupied inside the Fermi surface. And then you bring in your favorite quasi-particle with momentum p. So this is your quasi-particle momentum p. And you're going to ask that it undergoes a scattering process, okay? And it's going to scatter off the other excitations, right? So you bring in your particle, and then it's going to scatter off the other quasi-particles. So maybe it scatters off a quasi-hole here, which is momentum k. And it's going to, there's a particle sitting here already at momentum k, and these are going to scatter. So they have to scatter into empty states, and they have to conserve total momentum. So maybe they do something like this. This particle p goes here to some momentum, which we call p plus q. But the k guy has to go outside the Fermi surface, somewhere here to momentum k minus q, and has to conserve total momentum. I haven't, obviously my picture doesn't conserve momentum, but imagine that it does. And then I just use Fermi's golden rule. So the scattering rate is given by 2 pi times some interaction matrix element squared. This will be some screen Coulomb interaction, so let me just assume it's a constant. And then I have to sum over the fact that this state this state I scattered off better have a particle in it. So there's a Fermi function of Ek here. And then the states I scatter into, P plus Q and K minus Q, better be empty. So I have 1 minus the Fermi function. And then finally, I also have to conserve energy. And this is actually the kicker. It's not so easy to conserve energy, especially if your EP is small. If you're very close to the Fermi surface, you have no hope of scattering off a particle that's way inside the Fermi surface because you don't have enough energy to kick it outside the Fermi surface. Anyway, that's all automatically enforced by saying the initial energy equals the final energy. So that's Fermi's golden rule. If you actually do the calculation more carefully using diagrams, you get basically an expression like this. It's slightly different, but I don't. So let's just work with this. And so now we have to evaluate this. Okay, this is still a pretty complicated thing to evaluate, but there is a limit where the book does an honest job of it. I won't. I'm just going to ignore momentum conservation. It turns out it's not that important. In fact, if I had a disordered system, suppose I had lots of impurities, I can still then think about quasi-particles, but I don't have to worry about momentum conservation. So I just imagine I ignore the fact that I have various momenta and just simply integrate over the energies, okay? So what I do is I just replace Ek by E1, call this E1, call this E2, and call this E3, and the incoming energy I call E. So EP will go to E. Okay, so we just do that and ignore the fact that the momentum have to be conserved. You get this very simple looking integral, which is finally something that I can evaluate with the delta function of energy conservation. Now there's various prefactors that must appear. But one thing you know for sure that when you convert a momentum summation to an energy integration, you always get a factor of the density of states. And then you have to do some dimension counting to figure out that you also get a factor of the Fermi momentum to the power minus d in d dimensions. Okay, so now this is a simple integral. And what you find, say at 0 temperature, this vanishes as epsilon squared. So that's the key result. Gamma of epsilon, the scattering rate of a particle's energy epsilon, is epsilon squared. So as epsilon goes to 0, it's much, much slower than epsilon itself. So, and that's exactly what we assumed in all our calculations. And the reason this is happening is coming entirely from two effects. One is the Fermi statistics, which tells you that you cannot scatter a particle into another state that's already occupied. And the other is energy conservation. So the closer you get to the Fermi surface, the fewer particles you can scatter off, because you have to scatter them from inside to the outside the Fermi surface. So they have to be at least as close as you are, so you can give them some energy. And that's automatically computed by this integral, and you just get that. And if you do it at finite temperature, it vanishes as temperature squared. All right, so that's the basic justification ultimately for Fermi liquid theory, the fact that this is so small. And once you realize that, then everything that I've said in the last 2 lectures follows from that. So in particular, there's no constraints on Fermi liquid theory on how different this EP could be totally different from ET0. The ZP could be very, very small. That, what happens in the heavy fermion compounds, those things are really different from free particle behavior. But as long as the gamma p is small, you're fine. the Landau's Fermi liquid theory will exactly apply. Any questions? So I've just kind of skimmed the surface really, but the main ideas I think I've gotten across of a very beautiful subject with many books written on it and many connections to experiment. What I want to do, which I guess I won't finish, but I do want to do this because it's really quite important and beautiful of some of the things I'm going to cover later, which is something called the Latency relation. So, this is I won't be able to give the complete proof of this relation because it involves, again, a lot of technical stuff with diagrams. Here you do, there's a way of also proving it using Landau Fermi liquid arguments, but they're not as, they also involve a bunch of assumptions. So the Latency relation is simply something I said once earlier, that the location of the Fermi surface, so what we've seen here is that EP, in principle, you start out with some EP0, which vanishes at the Fermi level. And then you have all kinds of renormalization from the self-energy and end up with a new EP. How do you know the new EP vanishes at the same Fermi level? Actually, you don't. In fact, in a crystal, it doesn't. It could vanish at a different point. So, and where EP vanishes is precisely where the Fermi surface is, because that's when the pole crosses zero energy. So the actual Fermi surface is where EP vanishes, not where EP0 vanishes. And those 2 points could be different in a crystal. But in Gellium, they're actually exactly the same. And in a crystal, if you have interactions, the Fermi surface can move around, but it only moves in a way that preserves the volume. Okay. So the Latency statement is the following, that, well, I can just give you the final answer here. Yeah, the density of electrons, write it out here. Yeah, this is for spinless electrons. The density of electrons, bare electron, which is a given number. So we assume that we're keeping the density fixed as we're turning on the interactions. Then for free particles, it's just given by the sum over all negative energy states with EP0 here. But for interacting particles, it turns out it's given by the same expression, but with the interacting EP. Since the density is the same, it means the volume enclosed by the Fermi surface should be the same, or the area in 2 dimensions. Okay, so that's the Latency relation, which, well, I'm running out of time, which I'm going to sketch the argument for the proof of the Latency relation, but I don't think I have the time to do that today. Leave that for Friday then. So basically it involves computing the electron density from the Green's function. This is something we did already a little bit about, when we computed n of p. We did the same integral where we also integrated over p. Sorry, we didn't integrate over p. So this is what we computed. And this certainly changed. N of p changed because of the effect of interactions. But the fact that there was a discontinuity on the Fermi surface didn't change. Okay, but everything changed due to interactions for n e of p. But now I'm going to integrate over p. And my claim is if I do integrate over p, that is integrate over all of this, that's going to be preserved because of the interaction. So what's happened here, roughly speaking, you can just see it's kind of a sum rule on this distribution function. This was a step function like this. And the step function, the step got reduced, but that has to be compensated by an extra piece above p. So the area under this thing is the same. That's the Latency theorem. You may reduce the step, but then you have to have other pieces that make up the fact that the density remains the same. Okay, so that involves proving that in fact this quantity, once you integrate over P, doesn't change because of interactions. Provided, of course, it doesn't change by definition in the left. I mean, it's a question of how you put it. So we're going to prove that the quantity, this quantity here, is just equal to this with the new dispersion EP. So what this means is that if the density is the same, then the area under the curve EP equals 0 is the same as the area under the curve for free electrons. Okay, that's the statement anyway. All right, so it involves a few steps, which I don't have time to do today, and I'll do that on Friday. But any questions on Fermi liquid theory in general? Okay, then I'll stop here. So thanks very much, and we'll finish Fermi liquid theory next time and then start discussing the Kondo effect. Okay. See you on Friday. And I will have a discussion tonight at 9 p.m.